So in the previous videos we have solved non-sway frames. So from now onwards we'll solve the sway frames. So we are going to solve this frame using the moment distribution method. So let us look into this frame and understand whether this will sway or not. So I told you the only way to understand whether the sway will happen or not to first look into the support conditions, right? So we have only supports at A and D. There is no support at B or C. Henceforth, this portion can undergo the translation, which is horizontal translation. And next thing what we look into is the symmetry of the columns and the symmetry of the length of the columns, then the loading. Okay, then there is a horizontal force also. So it means what, this will definitely sway. First there is a horizontal force which is acting in this direction, it will sway. One of the important condition has been satisfied. Next thing is that there is no support at B and C. It means what, there is no restraint for the force being applied. Henceforth again the sway will happen, and you can see that the support conditions are also different. Support A is pin support, support D is your fixed support. Henceforth the sway will take place. Okay, so once we have understood that this frame is going to sway, we'll look into the loading conditions. We have a load of 50 kilonewton on column AB, and we have a load of 20 kilonewton meter on beam BC. Okay, on CD member there is no load. Okay, and you can also see the length of the individual elements. So BA or AB or CD is having a same length, which is 4 meter, and length of member BC, which is beam member, is 6 meter. And the next thing that you can observe is the I value. So here I is equals to 6 for beam and I is equals to 4 for both the columns AB and CD. Okay, so once we have understood this frame, next thing is that the very first thing that you can do is to calculate the fixed end moments. So you can develop the fixed end moments at AB, BA, BC and CB, right? So that's what I have done. So MFAB, MFBA has been calculated, and MFBC and MFCB is also been calculated. This is your point load. It means what, 50 into 4 divided by 8, that will give you MFAB and MFBA. Similarly, this is your UDL, 20 into 6 square divided by 12 will give you MFBC and MFCB. So once you solve for the fixed end moments, the next thing is to determine the distribution factor. Okay, so let us look into the distribution factor. We can consider only two joints, which are B and C. Joint B is having two members connected, BA and BC, right? So I have written over here. Now similarly, joint C is connected by two elements, which is CB and CD, which I have written here. Now let us try to understand the K value, which is stiffness value. So stiffness value for BA, as we know that the far end is pinned, henceforth this will be 3 by 4 into I value is how much, 4. So 3 by 4 into 4 by 4 will be the K value. Now similarly we can solve for BC, which is 6 by 6. So I am taking the summation of this, which will give me the joint stiffness. Okay, so joint stiffness of B is 1.75. Now similarly we can go for C. Joint C, this is CB is 6 by 6, CD is 4 by 4. Summation of that is 2. Now we can calculate the respective distribution factor for BA, BC, CB and CD. Okay, so once you solve the distribution factor, once you solve the fixed end moment, now we will divide this entire analysis into two parts. First part is called non-sway analysis. Okay, now we will consider that this will not sway. Okay, considering that this frame will not sway, we will try to define the moments. Okay, whatever the moments are there, we will try to calculate. In the next stage we will go for sway analysis. Okay, when we go for sway analysis, I have to explain something over there. Okay, so when we are going for sway analysis, we have to look into this figure. Now this is your frame, which is going to translate like this, and the translation is your delta value. Okay, now this delta value which has been translated will create some moments, right? So I have written what is the moment that will get created. Okay, now we already know if the far end is fixed, the value of moment that will be created, m dash values. Okay, I told you that whenever I use m dash, it represents the moments due to translations. Okay, So m dash CD and DC can be calculated. As we know, it is 6 EI delta divided by L square. Now the length of the member is 4, hence 6 EI delta divided by 4 square will give you the moment for these two. Okay. Now in case of far end being pinned, at the pinned end it will be 0. The moment will be 0. Okay. At the near end it will be minus 3 EI delta divided by 4 square. Okay, you remember this, which I have not derived you in the previous class also. Okay, but you have to remember this, that if the far end is fixed, the value of moments at far end and near end will be 6 EI delta divided by L square. In case of far end being pinned, at the near end it will be 3 EI delta divided by L square, at the far end it will be equal to 0. Okay, now you remember this. Now as I am saying that there will be a translation, but I do not know what is the value of translation, that is delta value, I do not know. Now in this case what I am doing is that I am assuming it to be 100. So here what I am doing is that I value is remaining same. He has not given you the E value, it means what E is also remaining same. So henceforth what I am trying to do is that I am assuming EI delta value. Okay. Assuming that EI delta is equals to 100, I can solve for MAB, MBA, M dash CD and M dash DC. Okay. Now see here, what I'll do, M dash AB, which we already know is equal to 0 because the far end is being pinned, so we'll write 0. M dash BA, which is this value, how much I have written here, minus 3 EI delta divided by 4 square, right? So I'm going to substitute EI delta as 100 in this equation. So 3 into 100 divided by 4 square will give you M dash AB. Okay, so once you solve the M dash AB, we can solve for M dash CD and M dash DC by substituting EI delta in this equation. 6 into 100 divided by 4 square, which is called 37.5. Now all these values which I have written over there are called as arbitrary sway moments. Okay, you can write this as arbitrary sway moments. Okay, anyhow these are not final moments. Okay, we cannot vouch for these moments, these are assumed. Okay, I have assumed the EI delta value, so all these values are arbitrary moments, these are not the corrected moments. So I can also say these as incorrect sway moments, incorrect initial sway moments. Okay, so anyhow, so what we'll do is that we'll call this as arbitrary moments. So now these values which I calculated, I'll be using it when I go for sway analysis. Okay, right now we are going for non-sway analysis. Now you will be confused, what is this sway analysis and non-sway analysis? What we'll do is we'll take this same frame. With this same frame, first what I'll do is I'll use only fixed end moments and I'll analyze. I'll use the moment distribution method and I'll calculate the end moments. Whatever the moments that I calculate are the end moments calculated from non-sway analysis, because I'm not considering that the structure is supposed to sway. Okay, that is my first condition. When you go for the next condition, which is called sway analysis, in the sway analysis I'm assuming it to be some value called EI delta. Okay, so instead of FEM, wherever we used to write FEM, there we are going to use this M dash values. Okay, so M dash AB, M dash BA, M dash CD, M dash DC value will be substituted in place of fixed end moment. Then again the analysis is being done, then the end moments are created. Okay, now we have moments which are calculated from non-sway analysis, we will have the moments which are calculated from sway analysis. I will tell you what will happen in after these two analyses have been done. Okay, right now what is the first step? As you remember, the first step is that you will understand whether the frame is sway or not. The next is that you will usually calculate the fixed end moments, then you will calculate the distribution factor, then you will assume some EI delta value, and then you solve for M dash values. Okay, these are called as arbitrary values. Okay, then we will arrive at the correct moments later. Okay, I'll explain that part later. Okay, this is what the first step is. Okay, I hope this is very much clear to you. Okay, now let us perform the non-sway analysis. So this part of calculation will be of non-sway analysis, where I'm not considering any sway moments, I'm only considering the non-sway moments. Okay, now as you know this table, the first will be joints, members, distribution factor, and then the fourth row will be of FEMs. Okay, so we already know the fixed end moments of MFAB, MFBA, MFBC and MFCB. The same thing I have written here, and we already calculated the distribution factor which have been written over there. Okay, and now we'll start balancing the joints. Okay, the first thing that you do to balance is that you first go for balancing of joint A, right? So as we know that joint A will be of pin joint, so henceforth we have to make it equal to 0. So to make it equal to 0, what we need to do is that if FEM at AB is 25 minus 25, we have to apply plus 25 here. So when you apply plus 25 here, we have to carry over half of that to the far end, which is BA, right? So 25 been applied here, and at the far end 12.5 has been applied. Okay, now the balancing of joint A and carryover has been completed. So this completes my first step. The next step is to go for internal joints. So we'll go for joint B and joint C. We'll start balancing joint B and joint C. Okay, now let us go to joint B. In joint B, what we do is that we'll take the summation of fixed end moment, okay, and this carryover moment. So 25 minus 60 plus of 12.5 multiplied by these respective distribution factor BA and BC. Okay, we'll write over here by changing the sign symbol. Okay, so this is the balancing moment which I written for joint B. Now similarly I can write for C also. Here 60, positive 60 is there. Okay, then there is no fixed end moment on the other side. So 60 multiplied by the distribution factor 0.5, and similarly 60 multiplied by 0.5 I am going to write here by changing the sign symbol. So 60 multiplied by 0.5 is 30. We have to change the sign symbol. It will become minus 30 and minus 30. So this completes the balancing in the first iteration. The next what we do is to carry over, right? So we already know the carryover system. If the far end is pinned, we will not carry over. If the far end is fixed, we will carry over half of the moment being applied. Okay, so in case of BA, 9.63 has been applied, we will not carry over to AB, so here it will be 0. So internally we have to distribute, which is from BC to CB, CB to BC. So from BC to CB it will be 13.095 divided by 2. I have applied to the CB. Similarly minus 30, half of that will be supplied to BC. Okay, now this process is done. Now we'll go for joint CD. Now CD I have applied minus 30, henceforth I have to apply at DC minus 15, because the far end D is your fixed end. Okay, so now this completes the first iteration. Similarly we can keep on balancing the joint B and C, because we have carried over. Because of that there will be imbalance created. So this value will be multiplied by the distribution factor. Changing the sign symbol, we'll write the balancing values. So I have completed all the steps, and I have taken the sum of all the moments in the column beneath every member. So I have calculated how much is my moments. Okay, you know the drill, you know how the process of this table works, right? So I hope this is very much clear. Now whatever the moments that I calculated here, I'll call them as non-sway moments. So these are the non-sway moments I have calculated, and I have drawn a picture for that to represent all the moments, right? So at joint A we know it is equal to 0. At joint B we'll have at BA and BC, BA will be positive, BC will be negative, and the value will be, or magnitude will be 54.76. Similarly for CB and CD, CB will be positive, CD will be negative, and the magnitude will be 35.85. At D it will be minus 17.93. Okay, so these are the non-sway moments which I calculated. Okay, in the next step what we'll do is sway analysis. Alright, so previously what we did was non-sway analysis. So in this table we are going to apply the sway analysis. We are going to calculate for the sway analysis. But when you are solving for sway analysis, I have told you earlier, when we solved for sway moments, those moments were your arbitrary moments, or they are assumed moments. So we cannot vouch for the accuracy of those moments, but still we are going to conduct this analysis. Okay, so I hope you all remember we have calculated m-AB, m-BA, and we have calculated m-CD and m-DC. So these are the values which I have got and I have written over here. Okay, next thing is to carry out the moment distribution method, and then we will determine the sway moments. The sway moments that I will calculate, I will call them as incorrect sway moments. I will not call them as corrected sway moments. These are incorrect sway moments. Okay, now look at this. This is the same joints, and then we have members, then we have distribution factor also remaining same, then we have fixed end moments. Okay, So as we know, the first step that we do is that instead of FEM, you can write this as moments due to sway. Okay, so I have written it as FEMs. You can keep it same, or you can change it to moments due to sway, because the moments that I have written are the arbitrary moments or random moments considered for sway analysis. Okay, so or you can call it as initial sway moments. You can call anything you want. Okay, so this I'll call it as moments due to sway. Okay, right. So first thing what we do is that we will balance out the joint which is pin joint, right? So the joint A is pin joint, but as we know, in the FEM also it is 0, henceforth I'll apply 0 only. The carryover will also remain 0. Henceforth this step you can avoid if you know already. Okay, so anyway, this step is null and void, so we'll remove it. Next what we'll do is we'll go for balancing joint B and joint C. So this is your joint B and this is your joint C. At joint B we have minus 18.75, right? So minus 18.75, on this side we do not have anything. The summation of this is equals to 18.75 itself. So 18.75 is multiplied by the distribution factor. Changing the sign symbol, I have balanced the joint B. Similarly for joint C also, what I'll do, I'll take the summation of these two. Here there is no value, here we have minus 37.5. We'll multiply with the distribution factor and write down by changing the sign symbol. Now the joint B and joint C is balanced, and you know the process of carryover from BC to CB is to be carried over, and for CB to BC is to be carried over. Similarly for CD to DC has to be carried over, but in case of BA to AB there is no carryover because the far end is pinned. Okay, so you know the next process. What we do after the carryover, this joint B and joint C are imbalanced, and the imbalanced moment are again multiplied with the distribution factors, respective distribution factors, and changing the sign symbol we'll write the balanced one. Okay, again the process continues, the carryover will continue, and you will reach to a point where the balancing moments will get into decimal values, right? Then you will stop your iteration, then you will conclude your end moments, right? So what I'll do, again I'll add all the values of any given column. Okay, then I'll determine how much is my end moments. Okay, so now after the sway analysis has been done, okay, this is your incorrect sway moments. So these are your incorrect sway moments. Now look at this. This is your joint A, this is your joint A, joint B, joint C, and joint D. So at joint A we already know it is equal to 0. At joint B, BA is negative of 14.4, BC is positive of 14.4, and when you go to joint C, CB is positive of 20.83 and CD is negative of 20.83, and DC is minus 28.411. Okay, so all these moments that I have calculated are incorrect sway moments. Okay, we will calculate the corrected sway moments now. Okay, now let us try to solve the final end moments, which are the correct moments. Okay, now what we had done is that in the earlier step we had calculated non-sway moments and we had calculated incorrect sway moments. So first of all, what we'll do is we'll calculate the reactions that are possible from the non-sway moments and the incorrect sway moments. Okay, now let us go to non-sway moments. In the non-sway moments, I would like to calculate how much will be the horizontal reaction because of the moments that we have. Okay, so this is the moment which is 54.76. As we know, if I want to calculate from A to B, so RA into 4 plus of 54.76 will be equal to 0, which means what? 54.76 divided by 4 will give you this value, which is minus 13.69. Okay, you try to evaluate by yourself. If you find any difficulty, you ask me. Okay, now we'll go to joint D. I want to calculate the reaction over here. Again, RD into this distance, which is 4, minus of 17.99 minus of 35.85. If I send these two to RHS, it will become 35.85 plus of 17.93 divided by 4 will give you this value, which is 13.445. And as we know, these are the moments which are, these are the reactions which are calculated by the non-sway moments. Okay, once this is done, what is the next thing we'll do is we'll go for incorrect sway moments. As I told you, the moments that we have got here are incorrect, they are not correct moments. So we will calculate how much is the reaction over here from the incorrect moments. So again, same, RA into 4 minus of 14.44 will be equal to 0. It means what? 14.4 divided by 4 will give you the reaction, which is 3.6. Now similarly we can calculate here also. So 20.23 plus of 28.411 divided by 4 will give the reaction, which is 12.6. 6160. Okay, so once you calculate these two reactions, next thing is that we will calculate a reaction only considering the external forces. Okay, so there is only one horizontal external force, which is 50 kilonewton, which is acting on member AB. So henceforth at A joint we will have reaction of 25 kilonewton. Okay, this is the first thing that you have to do. You have to calculate all the horizontal reactions by the non-sway movements. We have to calculate the horizontal reactions from the incorrect sway movements, and then we have to calculate the horizontal reactions from the external loading. Okay, once this is done, now we will apply the equilibrium equation. We all know the equilibrium equation. What is that? Summation of horizontal force should be equal to 0. So now we have known what will be the horizontal reactions, which is HA and HD, right? So the two horizontal reactions that will be developed is HA and HD. So let us try to understand what will be this HA and what will be this HD. So what we have done is that we have done a separate analysis for fixed end moments. We have done a separate analysis for sway moments. Okay, so the the moments which are calculated for the fixed end moments are called non-sway moments, which are actually the correct moments. Okay, so the moments which are calculated for sway are incorrect, right? So what I'll do is that I'll go over here. Now see here, in this I have written HA is equals to RAN plus of R dash A plus of R dash RAI I have written. Now let me try to explain you what are these values are. RAN is representing the reaction which is calculated from the non-sway movements. RA dash is representing the reactions which is calculated from the external load, and RAI is representing the reaction which is calculated from the incorrect sway movements. Okay, now let me substitute all the values over here. First we will substitute this RAN, which is representing the reaction which is calculated from the non-sway movements. So from the non-sway movements we have the reaction at A as minus 13.69, and then the reaction because of external loading is 25 kilonewton. Now at the incorrect, which is 3.6, but as I told you, this is not a correct value. So to correct that, what I'll do is that I'll multiply a constant which is called as correcting factor, you can say. Okay, so this is the correcting factor for sway. So as I know this is not the correct value, so 3.6 is multiplied by some coefficient called C. Okay, so now this completes my HA. Now similarly we can solve for HD also. What will be HD? HD is the reaction which is calculated from the non-sway movements, reaction which is calculated from the external loading, reaction which is calculated from the incorrect sway movements. So reaction which is calculated from the non-sway movement is 13.445 plus of the reaction which is to be calculated from the external load is equals to 0. We'll write 0, and RDI, what is RDI? Reaction which is calculated from the incorrect sway movements. Now going over here, which is 12.16. As I told you, these are incorrect in nature, so that's why I'm multiplying a correction factor here. Okay, now going back to this earlier equation, which is summation of horizontal force equals to 0. Here what I have to do, HA plus HD should be equal to 50. Now I'll equate these two. I'll substitute the value of HA over here in this equation, and I'll substitute the HD over here in the equation. This is what my equation becomes. Okay, now let me simplify this and calculate how much is the correction. So correction is how much? 1.6018. Okay, when I simplify this equation, this is what I'll get, which is 1.6018. Now what we'll do is, this value 1.6018 will be multiplied with all the movements in the incorrect sway movements. So I'm going to multiply this factor, correction value, this correction factor, to all the movements in the incorrect sway movement. So what I have done is that I have multiplied 1.6018 to 14.44, and I have written here these are my correct sway movements or corrected sway movements. So 1.6018 multiplied by 14.4, 23.06. Similarly 1.6018 multiplied by 20.23 will be 32.4. Similarly this value, again the correction factor multiplied with the 28.411 has been written here. Now again what I did is that I calculated how much will be the reaction because of these. Okay, the reaction which is calculated from these movements are 5.765. Again the reaction which is calculated from these movements are 19.48 at A and D respectively. Okay, now if you want to again go back and check in the horizontal equation, summation of horizontal forces equal to 0 equation, you will get the correct value. Okay, now these movements are your correct movements, these are your corrected sway movements, these are your non-sway movements. Now what is the next step to be done? So the next step would be this, the final end moments. So the final end moments will be summation of non-sway moments and the corrected sway moments. Okay, this is what you need to do. Okay, now what we'll do is we'll quickly write down what will be the final end moments. Okay, now let us quickly solve the final end moments. So what we do is that in calculating the final end moments, what we need to do, we have to add this non-sway moments with the corrected sway moments. So first we'll go to joint A. At joint A we will have MAB. So to calculate the MAB, what we need to do, we have to add the moment from the non-sway moments and the corrected sway moments. So 0 plus 0 will be equal to 0 itself. Now going to calculate MBA, to calculate MBA, what we need to do is we need to add plus 54.76 with minus 23.06. I'll get 31.7. So this will be my MBA. So this is my final end moment. Okay. Now similarly for MBC, MCB can be calculated. Now here minus 54.76 plus of 23.06 will give you minus 31.7, which is MBC. Now similarly for CB, CD and DC can be also calculated. So once you have solved these final end moments, we can solve for bending moment diagram, we can solve for shear force diagram, and you also calculate the reactions VA and VD. Okay, so this is the part which is left to you. Okay, you solve me and send your results. Now if you find any difficulty in solving this entire procedure, you can ask me the doubt. Okay, I'll quickly give you an overview of what we have done in this small video. First thing what we do is that we calculate the fixed end moment, then we'll calculate the distribution factor. After that we'll calculate the arbitrary sway moments, which are not correct sway moments. In that I assume the EI delta value. You can assume any value. I have assumed the EI delta as 100. So after solving the sway moments, what we do is that we'll do the non-sway analysis. In non-sway analysis, we'll perform the analysis by only fixed end moments. So once we calculate the non-sway moments, we'll write down the non-sway moments. Next is we'll go for performing the sway analysis or sway moments to calculate the incorrect sway moments. In that, the arbitrary sway moments which we have calculated, we'll substitute that in the row of fixed end moment, and we'll carry out the process and we determine how much is incorrect sway moments. So once we have determined the incorrect sway moments, we'll use the summation of horizontal force equals to 0 equilibrium equation, and in that we try to solve the correction factor. So once the correction factor is solved, we'll multiply the correction factors with the incorrect sway moments, and then we'll calculate how much is corrected sway moments. So once you calculate the corrected sway moments, we'll calculate the final end moments by taking the sum of moments calculated at individual joints from non-sway moments and corrected sway moments. That will give me the final end moments. So this is what the procedure to calculate or to analyze the frame which will sway in case of moment distribution method. Okay, so if you find any difficulty in solving this, you can ask me the question, or if you find any problem that you find very difficult to solve, you send it to me. I will try to solve it over here. Okay, thank you so much.